1.3. The masses of atoms, molecules and ions. Okay, so let's see what this means. See, if I am asking you to weigh, so what is the weight of this fluorescent marker? Maybe if I am weighing using weighing balance, it is supposed to be around maybe it would be around some 10 gram. So that much is the weight of this this fluorescent marker, right? So yeah. So suppose if I am asking you to weigh the mass of one atom, how much is the mass of one atom? We don't know. We don't know the mass of an atom, right? Because it is anyway, it is not 1 gram, or it is not 1 milligram, or it is not even 1 nanogram. See, maybe with our common weighing balance standard, like we can go up to milligram quantity, but not nanogram quantity. Of course, nowadays there are many sophisticated techniques are there, like scanning tunneling microscopy. So, like there are many techniques are there using which we can measure the mass of an atom. But now, now it is possible. But once upon a time, it was not a possibility, right? So, in order to measure the mass of an atom, okay, what is the requirement is? See, like what the scientists have done is they put a concept called relative atomic mass. Relative atomic mass. So the relative atomic mass is maybe, see, they took initially in initial period they took the mass of hydrogen atom. See, mass of hydrogen atom as 1. So the helium, it is actually 2 times the mass of hydrogen. So they put it as 2 atomic mass unit. Okay. So and the mass of other elements, they compared with the hydrogen. Suppose this is hydrogen, so this is helium, because this is 2 times the mass of hydrogen, and this is actually 3 times the mass of hydrogen. Okay, so hydrogen, helium, lithium, and then this is actually 4 times the mass of hydrogen. So this is actually beryllium. Okay. So that is how it is coming actually, like how much they compared it with the relative atomic masses, and maybe. So the concept is the relative atomic mass is in fact initial days, of course, they have used hydrogen as the reference and like first standard, but later on they changed it into 1/12 of the mass of carbon 12 isotope. In fact, this is more, very close to the mass of hydrogen atom. Mass of hydrogen atom. This is actually 1/12 of the mass of carbon 12. This is going to be the mass of. This is very close to the mass of hydrogen atom, and so 1/12 of the mass of 1/12 of the mass of carbon 12, they put it as, the scientist has put it as atomic mass unit. AMU stand for atomic and M stand for mass, U stand for unit. Okay, so this is nothing but atomic mass unit. Okay, so yeah, and now the scientists have done the mass of let it be atomic mass of lithium, actually it is going to be 7. So this is actually 7 into 7 times 1/12 of the mass of carbon 12. Okay, atomic mass of helium, this is actually 4 times the mass of 1/12 of the mass of carbon 12. Okay, so and atomic mass of let it be, maybe you can take in some another metal, some another element, let it be hydrogen, helium, then boron. Okay, let it be boron. So this is going to be atomic mass is of 5, So, yeah, sorry, not boron, let it be nitrogen. Nitrogen, it is a 14 atomic mass unit. This is the mass of nitrogen. So, this is actually 14 times, 1 by 12th of the mass of carbon 12. Okay, so this is how the relative atomic mass is coming. Actually, in fact, these terms, atomic mass, it is a relative term. We call it as relative atomic mass. Relative atomic mass. It is represented with the AR. Okay, and in fact, A, in subscript, we will put it as R. So R stands for relative. So this is a very important term. Exact calculation of atomic mass, it is a difficult task. It is an impossible task. Of course, nowadays there are some techniques, like a scanning, tunneling microscopy is there. Scanning tunneling microscopy, you can put a STM. Scanning tunneling microscopy is there. So these terms, using that, nowadays it is possible to calculate mass of an atom. But in old days, it was literally it was not possible. Okay, so that is it about relative atomic mass. Yeah. Now we need to find what is relative atomic mass and isotopes. Okay, relative atomic mass and isotopes. So, what are the isotopes? See, for example, if I am asking you, if I want to ask you, what is the atomic mass of carbon? So you may feel like, okay, it is a 12. Okay, 12 atomic mass unit. Okay, 12 is partially right, because carbon, it is going to have 3 isotopes: 12, carbon 12, C13 and C14. So if you are asking me the atomic mass of C13, it is going to be 13 atomic mass unit. So this is going to be 14 atomic mass unit. See, whenever an isotope comes, like for example, carbon 12, C13, C14, whenever an isotope comes, what we need to do in that case is, okay, for example, we have to multiply it with the relative abundance and we have to add it. You couldn't understand, right? I will show you with an example. For example, let it be chlorine. Okay, see, chlorine, it is going to have Cl. It got 2 isotopes, Cl35 and Cl37. So if you check the chlorine and its relative abundance, see, let this be the chlorine, Cl35, this is Cl37. So it got 17 protons and 18 protons for 17 protons for both, and number of neutrons, it is going to be 18. Here it is for Cl37 it is 20. So the nucleon number here it is 35, here it is 37, and its percentage of abundance. Percentage of abundance is, if you check the whole percentage of chlorine. So Cl35, it is present in 75% of the chlorine, it is going to be Cl35, and the remaining 25% it is going to be Cl37. So in this case, the atomic mass of chlorine is going to be, so 35 is the atomic mass of chlorine. So it is going to be 75 divided by 100 plus, it is going to be 37 into 25 divided by 100. Okay, so this is the one. So now, so it is going to be 0.75 plus 37 into 0.25. Now, okay, so it is going to come around 35.5 5. So this is the way we will be calculating the relative the atomic mass of carbon. The molecules, sorry, atoms, it is going to have isotopes. Okay, so this is the case. For a C12, it is we will multiply it to the 12 into relative abundance of carbon plus 13 into relative abundance of C13, 14 into relative abundance of C14. Okay, so this is how we will be calculating, and for some of the common elements, let's see what is the atomic mass. See, for example, hydrogen, it is going to be 1. Helium, relative atomic mass is going to be 4. Lithium, it is going to be 7. Okay, and and maybe boron, I don't know. Maybe boron, it is let it be sulfur. Sulfur, it is going to be 32. 32 atomic mass unit. Okay, so this is how the atomic mass unit and all it is coming. Now if I ask you to find the molecular mass, see, for example, H2O. How to find the mass of molecules? See, here actually H2O molecular mass is equal to 2 into 2 hydrogen atoms are there. We will multiply it to the mass of hydrogen, it is 1, plus 1 into mass of oxygen, that is going to be 16. So you will get 2 plus 16, so that is going to be 18 atomic mass unit. Now let it be for if I ask you for CH4. Okay, you are not visible, so here I will draw CH4. Yeah, we will see how it is coming. For atomic mass of carbon, it is 12 plus 4 into atomic mass of hydrogen, it is 1. So it is going to be 12 plus 4, it's going to be 16. So 16 is the atomic mass of CH4. Okay, atomic mass unit. Of course, we need to write, we are supposed to put the unit, so that is nothing but atomic mass unit. Okay. So now we need to know what is the formula mass. See, this is in fact similar to atomic mass. I will tell you in what situations you will be telling atomic mass and formula mass. Molecular mass and formula mass. So, see, this is an individual molecule. Same way, carbon dioxide is also an individual molecule, and CH4, it is also an individual molecule. Formula mass is, for example, sodium chloride. So Na plus Cl minus. Okay, Na plus Cl minus. So see, this is sodium chloride. So, or like a potassium chloride. In these kind of situations, instead of a molecular mass, we will use the term formula mass. Okay, so this is one of the concept. This is one of the very important concept. Okay, please mind it in your. Please keep it in your mind.